have Benny Applebaum, even if only virtually, tell us about advisor verifier prover games and the relation to information theoretic cryptography.
Right. Thank you. So first, let me thank the organizers. Like I looked at some of the videos online, and it looks like a very amazing event. So thanks for organizing this workshop. Although unfortunately I couldn't make it. And so this is the first time that I'm going to give this that I'm giving this talk. So please comment or feel free to interact during the talk. Whenever you have a question, I'll be happy to hear comments. Also by email after that if you want. And this is a joint work with my student, Oded Nir. And the reason that I highlighted here the word assumptions is that one of the points that I want to make, so this talk has more questions than answers. And one of the points that I want to make is that for some parts of cryptography, it's not even clear that we need assumptions. And like an alternative, I guess, title for this talk is the question, under which assumptions cryptography really needs assumptions. This is for the meta complexity workshop next year. So I'm already ready for this. So just to illustrate this point, let me take a look at Pagliazzo's world. And right, I think that as far as I could see by the abstract, we talked a lot about all these areas. We can discuss whether we should put NISC in Cryptomania or Minicrypt, and whether I guess Pestilent even exists and so on. But note that I think, as far as I could see, we didn't even talk during this workshop, and typically also in cryptography conferences, we don't really talk about Algorithmica. So let me remind you, Algorithmica is the world where P equals 2 NP. And we do not talk about it for a good reason, right? We have this kind of meta theorem that says that, interesting crypto really needs one-way functions, right? Starting with the work of Pagliazzo and Luby, and we have many versions of this theorem that were proved in different contexts. And indeed, you can see in this map, right? Algorithmica is also known as the Great Sandy Waste, and the Deadly Desert, or the Impassable Desert, and so on and so forth. So it's really a boring place to be. But I want to mention that we have some constructions, say Minicrypt, for example, garbled circuits, that we do not know whether they really belong to Minicrypt or actually they belong to Algorithmica. Another example, even in Cryptomania, I'll talk about it later, this notion of succinct secret sharing. So we know how to build it in this land, but it's not even clear that we need any assumption for it. And there are other examples even in Opustopia. So I'm not going to question this theorem, but I just want to make the point that we do not have a full proof for this theorem for some of the primitives that we have. So there's still open questions even in this domain, which seems to be close, I don't know, since the 90s, I guess. Okay, so let me be more concrete. So let's start with private information retrieval. So we heard about it in Daniel's talk. Right, we have a client, we have a server who holds the database, and this client wants to access the database without revealing the location, right? And I'm going to think about a single round schemes. And it will be convenient for me to think of this database as a truth table of a function. So this is capital N bits, which means that it represents an N-bit Boolean function. And since we are going to talk about information theoretic variants of this problem, okay, so accordingly, the index is just an N-bit string, right? It's an index in this huge truth table. And since we are in the information theoretic setting, I'm going to assume that there are several servers, where each server holds a copy of this function f, and this client is allowed to access each of them separately. And when we talk about privacy, we mean that the query, say, to the first server is distributed independently of x, right? So this client has coins, and if we restrict our view only to the first query, to the first server, we cannot tell anything about this string. right? So this is the standard notion of privacy. Good. So I want to focus on the communication, right? I don't care about computation here. And we can ask, can you get poly-n communication? Not that this is like lowercase n, so this is like polylogging the size of the database. Okay? And to make my life easier, at least from a lower bound perspective, I'm going to restrict this problem to the case where I have only a constant number of servers and the answers from the servers are just a constant, or say even single bit. And this setting is known to be essentially equivalent to the case of locally decodable codes, which are binary. Okay, and I'm going to think about the question of communication here. Translate very nicely to the question of the length of such codes, the best possible length. So what do you know about this question? So the lower bound is, as all the lower bounds in this talk, is going to be fairly pathetic, right? I mean, so n plus omega of n, so this n is trivial, right? I mean, because we know that you have to kind of communicate at least n bits, because your input, otherwise, the answer is not well defined. So an n bit lower bound here is trivial, and we can get an additional linear amount of bits in n, where the constant really depends on this k, the number of servers. And although this lower bound is pathetic, it's highly non-trivial to prove it. And in fact, in the upcoming talk, there is a new result that proves 3n lower bounds for this very special case of 3 server single bit answers. So even this thing is extremely complicated and requires some new combinatorial insights. Good, so that's the lower bound. What's the upper bound? So the upper bound is a sub-exponential, right? It's 2 to the square root of n. And this is based on the matching vector approach that was introduced by Ekanin. Okay. So that's the best upper bound, that's the best lower bound, and we see that there's a huge gap, and we cannot rule out the poly-n solution. I should mention that if you are willing to assume to make computational assumptions, right, to relax security to computational, then we actually get a poly-n solution or polylogging the size of the database. This is a Gilboa and Ishai, right? Just based on a sufficiently strong one-way functions. Okay. But again, it's not clear whether these one-way functions are really needed. I mean, in a sense, we kind of throw in a computational gadget without knowing whether, fancy combinatorial ideals can actually solve the problem without using complexity theoretic tools. Okay, let's move on to the next primitive. So this is a generalized secret sharing. So if here our client holds a secret, he's going to distribute the secret across these servers. So we have n servers this time, not a constant number of servers. And want to make sure that there are some authorized sets that should be able to recover the secret given their shares, but unauthorized sets should learn nothing about the secret. Right, and the way we specify authorized and unauthorized set is based on this function. Right, so we can think about the input to the function as a subset, and the function tells us whether this set is authorized or not. And since a subset of a non-authorized set is also non-authorized, and a superset of an authorized set must be authorized, we can assume that this function is bound. Okay. So again, we can ask, what is the best possible solution? And here I'm going to measure, again, I don't care about the computational complexity. I'm going to measure the quality of the solution as the size of the maximal share. Okay. And we can ask, can I get a poly-n share size? So here the lower bound is not even linear, it's n over log n, right, due to CMAS. And the best upper bound is currently 1.5 to the n. So for a long time it was 2 to the n. Then Tienren, Vekutanatan, and Hotekui were able to push this a little bit, and then after a sequence of work, this was shared to 3 over 2 to the n. Okay? This is jointly with Oded, the same student who was the author of this paper. So again, almost linear lower bound, exponential upper bound, and we do not know where the truth is. And again, if we throw in our fancy cryptographic tools, so we have this new result with Amos, Yuval, Eyal, Tienren, and Vinod, that gives us a solution based on sub-exponential strong RSA. Okay? So we can get this kind of solution if we are willing to make, in this case, Cryptomania type assumptions. And again, it's not clear that this is really needed. Right? I mean, it's not even clear that one-way function needed. Maybe we can do this unconditionally. Good. Questions? Remarks? Okay. Let's move to the third primitive. So this is a fully decomposable randomized encoding, and this is also known as Garblin schemes or Garbled circuits and private simultaneous message protocols. It has many names, or randomizing polynomials. And here again, we have n servers. Each server is going to hold a single bit. Okay. In addition, these servers are going to have access to a random string, a joint random string. And based on these inputs, right, say the first server looks at its input, the random string, and it computes some message and sends it to the client. Now the client sees all these messages. Yes. Someone
sneezed.
Ah, okay. I was hoping for a question. I can answer this.
So then, is this for like worst? So like we want to find like the worst case choice of like F.
Yes, yes. I'm assuming that this is kind of, I want a solution that works for every F. So in a sense, this is worst case over the Fs. Very good. Other questions? Okay. So let me define this model. So again, so the first party looks at X1, the random string. The function is public in this case. And they send the randomized message. And this client who sees these messages but doesn't see the inputs or the string should be able to compute the value of the function in the point X, but nothing else. Okay, so this is, and we can define the privacy in a very natural way. So again, we can ask, can we get a poly-n, right? And then I'm going to measure the maximal communication complexity over this channel. And I can ask, can we get a poly-n solution? And again, here, the lower bound is very weak, n over log n, basically. This is Marshall and friends. And the upper bound, this is Baimel and friends, is basically 2 to the n over 2. Okay. So again, huge gap. And in fact, here I don't even know how to do it computationally without throwing in some really like crazy machinery, like ideal obfuscations or things like this, right? So, you know, I don't know. This is this lives in a fantasy land or something like this right now. Good.
Sorry,
so we have. Oh, yes, please ask.
I asked a lot of wrong questions. So this is like for every like a monotone function, like every like this author like every like a access part. This is also like a worst case over like a access part. Like
the worst case over what? Over the functions?
But it's not quantum, these are general functions, not necessarily.
Yeah, it's like the it's like a
that is secure computation.
Like I mean this share like this secret sharing like sorry, probably this is a question about like the last slides like this secret sharing scheme like we're considering here like this like access this like author like this like structure of this authorization set.
Right.
This is like we're considering like arbitrary general like authorization like a structure or.
That means that is that worst case over access pattern.
Yeah, it's this worst case over access pattern.
Yes. Let me say a few more words, and then if the question is still relevant, I'll try to answer it. Okay. So let's try to compare these models. I think that it's
sorry. Go ahead, go first. Just a quick different question. So on the previous slide, why did you say Cantor computation? Like, why doesn't the Yahoo Garbled circuit solve the problem? Is it because the function?
Because this is an arbitrary function. It doesn't have. If you have a small circuit, sure, you can solve it using Garbled circuits, and even there, I don't know whether a one-way function is necessary for gobbling the circuit, but here this is the whole talk. All my functions are kind of represented by truth table, and I could actually give the talk also in a variant where functions are in P, and I think that there are kind of, in a sense, the current setting where we talk about truth tables is more basic, and therefore I attack this. But you'll see at the end that there are some interesting questions also for this, the variant where functions have efficient representation. Okay.
Sorry, I might have not just understood this model. So so there's like some function that's known in advance, and where do the servers get X? How do they decide the X?
So think about an external party who publishes F. So everyone knows F. Here F is public. Okay. And this outside entity, this external entity also gives the servers the inputs. Okay, so these guys get the input, just like in when you want to encrypt, someone gives you the input to the user, or someone gives you in an MPC, someone gives the input to the parties. Okay.
And where does the Dvir-Gopi result fit in here? Is it just like not as optimal as like the computational PARs that we have? Because I'm just kind of wondering, is it
here? Here, I don't know how to use Dvir-Gopi to get something in this world.
Okay.
Okay.
Maybe
it's possible. This is a very good question, but we don't know how to do it. So let me try to put the models one next to each other and try to see for a second how they relate to each other. So in a sense, there are very different models. So, let's start from the last one, right? I mean, here all the information flows from the servers to the clients. And we want to kind of keep the inputs of the servers protected. And the function is public, right? I mean, everyone knows the function. In this model, actually, the servers have no input, right? I mean, the information flow from the client to the servers, right? And the function is public, but now it's kind of indicates what are the access structures that are, that should be able to recover the output, right? As opposed to kind of, here we have some sort of computation over the private data. Here we don't compute anything over private data, right? The function just tells us which parties should be able to recover the value. And here, this is completely different story, right? I mean, here we have a bidirectional communication. So, the information flows in both directions. The function is private in this case, right? I mean, the client does not know the function. If he knows the function, then, he doesn't have to communicate with the servers at all. And we want to kind of keep the privacy of this input X, but once we put the communication complexity requirement, it also means that in a sense, we somewhat hide some information about this function as well. Right, so we have two sides of hiding in this case, whereas in all the other cases, we have only one-sided in a sense, right? Either we want to protect the client or we want to protect the servers, and you see the information flow. It's very different. So this seems to be like three different games. In all these cases, we have upper bounds, which are either exponential or sub-exponential in the case of PIR, and the lower bounds are almost linear, right, or linear in the case of PIR, right? So very big gaps, and maybe some of us are used to seeing these kind of big gaps, right? I mean, when we talk about say circuit lower bounds, but here, unlike the case of complexity theory, we don't even have like non-constructive lower bounds. So, take the function at random or use a worst case function or whatever, we still don't know how to prove anything. And another annoying thing is that we do not have general reduction between these problems. So, we know that NP is likely to, or we believe that NP is different than P, and we know that it's going to be very hard to prove it, but at least we know that all the NP hard problems are equivalent, right, up to polynomial reductions. And then we don't even have an equivalence, so we cannot kind of point out to a single assumption that implies the hardness for all these kind of things. We can make different assumptions for each of these primitives. Why should we care? So there are several reasons. These are basic questions, and they typically give like the solutions that we do have are actually very, very simple and clean in some sense. In some scenarios, they're even more efficient than the computational solutions. Also, these kind of questions kind of appear also in advanced primitives. So many advanced primitives are just, complicated versions of these simple primitives. I could write here a longer list. And the hope is that once we get good understanding of the ideas, of the problems that appear in this level, we'll also have better ideas of how to solve the problems in the more advanced level. And in fact, I can say that the RSA result that I just mentioned, indeed, it is based on some insights that were developed while working on the information theoretic variant of the problem. And there are many other examples for this kind of methodology. And finally, this kind of, these gaps actually highlight some basic things that we do not understand. So in a sense, it's easier for us to jump and throw in our fancy computational assumptions, but we should remember that, in some cases, we don't even know whether these things are really inherent. And, you shouldn't use, morally, you shouldn't use a PRF when you can use a pairwise independent hash function. Right, the same thing here. I mean, these heavy hammers, if they are not justified, we shouldn't use them, or at least we should know that they are not necessary for these tasks. Good. So hopefully I convinced you.
Any question?
Yes, please.
To what extent that these are toy versions of this advanced primitive? Because advanced primitive, when it's encryption and read, we do know that we only care about functions that have short representation, has a circuit representation.
True. So first of all, as I said, I said previously, so I could phrase all these questions for efficiently computable functions. For example, for efficiently computable functions, monotone functions, we have secret sharing based on monotone circuit, based on one-way functions, and we don't know how to achieve it information theoretically. This is still open. Similarly, here, we have Yao garbled circuit, as Daniel mentioned, but we do not know whether you can do it information theoretically. And the reason that I'm looking at this general function is that typically when you solve, if you make progress for kind of truth tables, you can lift it up and actually get some progress in the circuit model or more advanced models. And I think that the truth table setting is in a sense, is cleaner. Because one of the things that kind of make the problems when you look at the more advanced primitives, one of the things that I think make the problem harder is the fact that you look at circuits, right? Or you look at computational efficient, on efficient computation, and this is an object that we do not understand, right? Computational, efficient computation is a mystery. And when we look at these kind of versions, I kind of throw away all the computational requirements, all the computational restrictions. I don't have to understand circuits in order to answer this question, either in the affirmative or to the negative. This is how it seems. Good. More comments, please. Okay. How much time do I have, by the way?
5 to 10 minutes.
Okay. Let me try to actually tell you what we do and give you some hints about it. So we introduced a new hypothesis, and we show that it actually implies a single hypothesis. It implies polynomial law bounds for all these primitives. You'll see in a minute, but this kind of new hypothesis kind of is related to a classical subject in computer science, the space query trade-offs that you can get. But it's kind of the twist is that we take it into the interactive proof setting. And by using this kind of tool, we also get new insights about the differences between these primitives. We can unify some of the existing law bounds. And we can also show that some law bounds cannot be unified, right? We get some sort of separations. So let me tell you what's the new notion. So this is a standard setting of interactive proofs, right? We have a verifier, we have a prover. The prover claims that f of x equals to 1, and the verifier should either accept or reject. And I'm going to make the following twist. So the verifier does not see the function. Okay? There is an advisor, there is a third entity, an advisor that wants to help the verifier. This is a trusted advisor. The advisor gets the function f. It generates an advice. Then the verifier gets x. the advisor dies after it generates the advice. The verifier gets the input X. And then based on this input and the advice, you should make a single round of interaction with the prover and decide whether to accept or reject. Okay, so that's the model. And some default, so all parties are computationally unbounded. And for this reason, as long as I'm keeping this default, I cannot talk about a fixed f, because if the function is fixed, then the verifier can just compute it by himself. Okay. I'm going to assume perfect completeness, constant soundness, and I'm going to assume that the advice is a one-time advice. So you cannot reuse it over many inputs. So this is the model, and the goal is to minimize the communication, right? The sum of the bits. So let's play with this model a little bit. So first of all, if I throw away the prover, what do I get? Let me assume that you said the answer, because I can't hear the shouts. So we get a one-way communication complexity model, right? One party holds F, the other party holds X, and there is just a unidirectional communication. And we know for this model that there is an exponential order. Right? That's actually easy to prove. What happens if we switch from a general prover to a trusted prover that gives us an access to F punctured at the point X? So we are not allowed to ask about the point X, but we are allowed to ask on any other points, and we get this Yau's black box model. And here again, we have exponential lower bound. What happens if we require the A to be reusable? Then this turns to be closely related to memory checking, okay, to online memory checking. And again, in this model, there is a lower bound, which is exponential. On the other hand, what happens if we relax the model and allow more interaction? So it turns out that this model corresponds to non-uniform delegation. This is in the Magel paper in some of the hidden sections. And there they show actually that you can get polynomial communication in a quasi-linear number of rounds. Or more generally, if F is a d-depth S-size circuit, then you can get this, then the communication is polynomial in the depth and logarithmic in the, polylogarithmic in the size of the circuit. And this is also the complexity of the verifier, right? So this is kind of a non-trivial statement. Good. So what happens when we have a single round? Can we get polynomial communication? So the answer is yes.
Benny?
Yes.
What was the reusable point about A? What do you mean by reusable?
Reusable, I mean that you can get a single advice and then the soundness remains valid even if kind of the prover and the verifier play the game again and again with different X's. So in a sense, right, the advice is kind of generated with randomness, and this randomness can be used only once, right? Otherwise, it's kind of being leaked to the prover. Okay, so here's the solution with polynomial communication, right? I mean, the advisor defines the multilinear extension of F, and he gives 1 point of this multilinear extension, one random point. And now we can basically sample a random line, plant this point in a random location, get the answers, check consistency with the advice, and interpolate the value. Okay. And we get soundness of 1 minus 1 over n, but we can repeat, and we'll get the overall communication is going to be polynomial. Right? So now that here the prover speaks a lot. So since I want to prove lower bounds, let me restrict the prover to be laconic. So the prover can send only a constant number of bits. And here comes our hypothesis. We assume that the hypothesis says that this prover laconic AVP cannot have polynomial complexity. They have super polynomial complexity. And the theorem, which is really simple to prove, I'll show you the proof in 1 minute. Any polynomial solution for any of the above primitives will imply a prover laconic AVP with polynomial complexity. And this means that if you believe in the hypothesis, then you'll get a super polynomial lower bound for pairs, secret sharing, and the decomposable randomized code. So the proof idea is kind of based on this paradigm of translating secrecy to soundness, and it appears in many, many works. I think that you can even trace it back to the original paper on interactive proofs. So the transformation is not going to be very exciting. Let me show it to you. But let's start with pair. So we know that this pair, let's denote by Q1 the query that the client sends to the server, and by R1 the answer. So the advisor is going to sample one peer query and one peer answer. And remember that, when we look at a single query, its distribution is independent of the input. So this can be done ahead of time. Now the verifier who sees X can kind of sample these queries conditioned on the original query that was sent by the advisor, get the answer from the laconic prover, and then check consistency and accept or reject, right? And this is, in fact, the previous example that I showed was a special case of this transformation. What happens with secret sharing? Again, very simple. So we have this secret sharing scheme. So the advisor is going to give us all these shares and the secret. The verifier is going to send the secrets, the shares that correspond to the input X. And the laconic prover should be able to recover the secret, and the verifier accept if the prover did it properly. Now I want to point out, so super simple, soundness is immediate here. I want to point out that here in this case, we have a 1-bit answer. The verdict depends only on the advice and on the answer, but it's independent of X, okay? And the query itself has a very nice, simple structure. It's decomposable, right? I mean, so, each block that I'm going to send depends on a single input bit of X. It's also monotone in the sense that if I'm looking at an X which is larger than the original X, then I'm going to send more information. Actually, we have to define monotonicity in a slightly more careful way, but for now it's okay. So we have this secret sharing that implies all these things, and let me mention that when we have all these properties, we can actually talk about a single function F. Now it makes sense, and the question is well defined. Similarly, I'm not going to show you this transformation. This is an exercise. But here you see that we get the first 3 properties, decomposability, 1-bit answer, input independent verdict. But now we don't get monotonicity. Instead, we get this input hiding property, which means that I can run this interaction without letting the prover know what X is. So for the purpose of soundness, I can assume that the prover knows X. But for like an honest prover, I can actually hide X from the prover. Good. So this gives us some kind of way to compare between these primitives. Right? You see that peer gives us an AVP without any additional properties. And this kind of means that in a sense, maybe a peer is easier to achieve, right? Because it implies less restricted AVPs. And it is at least based on the current bounds that we have, right? I mean, the peer is to the square root n, or these things are exponential in n. Also, if you look at these properties, there's a missing a particle here, right? I mean, there should be some primitive that implies all these things, which only the first 3 properties, and indeed, you can fill this block by using what's sometimes called conditional disclosure of secrets. So, do I have 2 minutes, Yuval? How are we doing with the time?
2 minutes.
Yeah, okay. 2 minutes. So, what happens? Can we unify lower bounds? So we can prove very simple counting-based lower bounds. Basically say that if the advisor sends A bits and the prover computation is taken from a class G, then A times log G is at least 2 to the n. And this implies some very, very weak very weak lower bounds on the general thing, which basically breaks whenever B is n bits. But just by using this simple lower bounds, we can actually recover existing lower bounds in all these domains. So at least counting-based lower bounds can be induced by this general primitive. What about the best known lower bounds? So in the secret sharing world, the best known lower bound is due to CIRMAS, and use some complexity measure that is introduced by CIRMAS. In the decomposable randomized encoding world, the best lower bound is based on the Chikor's complexity measure. And it would be very nice to unify these things, but we can show that they cannot be unified. In particular, we come up with a function for which it has a maximal or almost maximal CIRMAS complexity measure, but it has very cheap CDS and therefore cheap AVP. In fact, if we allow us to use partial functions, then it can be even linear. So this is a quadratic separation, which is the maximal that you could hope for. Also here, same thing. I mean, we can come up with a function that has a high complexity measure under this measure, but very low complexity measure according to CDS. So let me conclude. So all these basic information theoretic primitives, they look different, but they all kind of imply that you can decompose computation into an online and offline part. We introduce this new model, a single hypothesis that implies a super polynomial lower bounds. The transformations themselves are kind of simple, but the main, I think, interesting part is the definition of this model. It induces some partial order over these primitives, and it unifies some of the existing lower bounds. You also get some separations. As I already mentioned, in the future, it will be interesting to scale down these things to P, and there are interesting questions about this thing that I don't have time to mention. And more generally, come up with more, maybe conditional lower bounds, or at least relate them to existing questions. Thanks.
Really interesting. While Prashant is setting up, take another quick question. Someone else. So maybe let me ask. Then in the other direction, so this new model can be used to unify lower bounds, but it does not serve as a barrier, right? Because you don't need to prove lower bounds in this model. Sure. What about the other direction, a common ancestor, all these primitives that serves as a barrier?
So let me give you a common ancestor. I'm not sure, but I think that the most easier challenge, okay, in this domain that we don't know how to solve, is for CDS that I didn't even define, prove that the messages should be super constant. Right? We do not know that, right? I mean, so the other things we could prove kind of linear lower bounds there, even super constant is open, and this is an intriguing question. I'm not sure how hard it is, but for now we couldn't do it. That's kind of the immediate challenge.
Thanks. Yeah, quick question, very once.
Benny, I don't know if you said this, but is there some dream version of a locally decodable code that would suffice for that, like a binary locally decodable code that would suffice for a positive result?
So, yes. So whenever I say peer, you can think about locally decodable codes. I said polynomial, think about quasi-polynomial length for locally decodable codes. The constant query is a binary alphabet.
Okay. Thanks again, Benny. For those who missed